Okay. Morning, everybody. Hope everybody's doing well today. I've got a little visitor here for my class, so we'll see. He's only here as well as long as he behaves. So you gonna behave yourself? This is Charlie, and he's getting bored watching Paw Patrol or whatever. So here he is. Uh, the pleasures of working at home. Okay. Now what is going on over here? Okay. Come on. There we go. All right, so yesterday we did Q. We talked about the equilibrium quotient as a tool for determining if your system is going to move either left or right during an equilibrium. And so let's do an example question as we are here. So for this reaction, we have a solid that labeled A. We have a gas, and then we have two gas products. So watch out for that solid. Remember that solids do not affect equilibrium. So is the system at equilibrium if K is equal to 25? So we need a Q equation, which is going to be our any aqueous or gaseous forms raised to the power of their coefficients. And I am not going to include not A because it is solid. Does not matter what the concentrations are. Okay, so let's punch in our numbers. We have a 30 over here, and that's going to be squared, so it's like 900, I think. And then we have a 2.0, which is also squared, so that's 4. So 900 divided by 4 is 450 divided by 2 is 225, I believe. So 30 squared divided by 2 squared divided by 4. Yeah, 225. So that's 225. That, of course, is much, much larger than our K. So 225 is bigger than 25. So which reaction? So not equilibrium. And which reaction is favored, the forward or the reverse? Let's think. We want to reduce. We need to reduce this number. Needs to come down, which means we need to bring down our numerator. And to bring down our numerator, which is bringing down C means we need to shift this way. We need to bring it down. So the only way to bring down C is to bring up B, and that's a shift to the reverse direction. So the reverse is favored. We have extra product right now. So which concentrations are increasing and which ones are decreasing? So B is increasing. And A, but A is a solid, so it's a little weird. And C is decreasing. So we have too much B, too much C, so that's going to be decreased. Okay, let's check this next one out. This one looks a little more complicated. Sometimes they just throw a lot of numbers in just to make it hard. So there exists an equilibrium if 5 moles of this and 5 moles of that and 0.2 moles of O2 are in a 2-liter container. Find K for the reaction. Would the system be at equilibrium if blah, blah, and blah? If not, which reaction is favored? So this is a two-step question. First, they want you to do a K calculation, which has the same organization. And then, so let's do that. It is a 2-liter container, so we are going to be talking about a concentration of CO2, which is 5.0 divided by 2.0 liters. We are going to be talking about a concentration of CO, which is equal to 0.20 divided by 2.0 liters, and a concentration of O2, which is going to be equal to, oh, the same, 0.02 divided by 2.0 liters. Moles. So that gives us our concentrations, 2.5, molarity. Excuse me, sir. Thank you. 0.1 molar and 0.1 molar. I love 0.1 molar. It's very easy to work with. Okay, so punch that into our calculator. 2.5 squared, our K calculator that is. 0.1 squared, 0.1. It's pretty straightforward. Question here, or calculation, divided by, stop that. Okay, so we get a pretty big K. We got 6,250 is equal to K. So now doing the same calculation, but for Q, remembering that the equation is essentially the same. So carbon monoxide, O2. Okay, so let's punch in the equations, that the values they gave us. So we have 15.8, and we're squaring that, divided by 10.0 squared times 0.25. And this looks pretty likely that it's not going to be at equilibrium. That's just my guess. That doesn't look like 6,250 to me, but I might be wrong. Yeah, 9.98. So 9.98. Excuse me. Stop that. So essentially 10 if you round. So 10 point for a two decimal value. Well, they did give us 3, didn't they? Okay, so 9.98 in this equation, 9.98. There's a 25 there. So that is 2 significant figures, so whatever. It doesn't matter at this point. 10.0. 10 point. Okay. So it is not at equilibrium. The Q is much smaller than K, so there will be a shift to the right to try to compensate. Okay, so we'll leave it there, and then I'd like to look at the graphs today so that we can sort of put the last nail in this equilibrium unit before the weekend. It is a long weekend, so there will not be a class tomorrow. I won't be posting anything tomorrow, other than maybe an assignment, but we'll see. Maybe I'll post some more tutorial videos for the equilibrium questions that I've been promising you. So we'll look at that. So in this last section is one that is a pre-established little unit here. So it's pretty straightforward. Thank you. So the graph we will be studying in this lesson illustrates actual experimental data for the NO2 N2O4 equilibrium. We will assume that the system was at equilibrium initially before the stress was applied, and after an instantaneous change, the system was allowed to reestablish equilibrium. The reaction is this. Notice there's a couple things that we need to notice here, that there are some, all right, I'm just going to clear this page, buddy. Clear the page. Okay. We notice that it is a exothermic reaction. So this is exothermic. And we notice that the gas concentrations, notice that there is an unequal moles of gas. What is wrong, Grumps? You can draw. Okay, so when we are interpreting equilibrium graphs, we can look at a couple of different things. Here we are going to look at the change in rate over time. And from looking at the change in rate over time, we can actually identify what kind of changes have happened to your system during that chemical reaction. So for example, if we see a graph that looks like this, where there is a giant sort of speed bump here, where suddenly there's an increase in rate, then this suggests that you have added some sort of reactant. And then that increase in rate will actually come back down as equilibrium is reestablished. If we were to remove a reactant, we would see sort of a speed drop, and then that chemical reaction would respond by refilling, responding to that loss of that chemical. And in the end, you would actually notice that the drop in rate would actually only be minimal. So we would have at the end of the day, there will be a decrease in rate over here because you have removed some chemicals, but that rate is only a small drop compared to the initial drop before equilibrium is re-established. So these little spikes, this is going to be your stress, right? And then this smooth line, this is the shifting, and then this is the new equilibrium. So stress. Another word is change, and then new equilibrium. Okay, so graph A, we have initially the reaction is at equilibrium initially, then both both forward and reverse are equal. Then a bunch of NO2 is added. You get a big spike in rate, and then as that excess NO2 is consumed, a new equilibrium is reached, and that new equilibrium is at a higher rate. So we do notice that it is a higher rate than the initial one. So rate has increased because overall you do have more matter in there, and you have more of the reactant matter. So the rate of reactions is increased. However, as more product is formed, the rate of the back reaction also increases. So overall, if you have a vessel with excess, with a lot of reactant in it, then it's not that then overall the rate of the forward and reverse reaction are at equilibrium higher than a vessel with less reactant in it. Something to consider if you're thinking about, balancing these sort of things, comparing reactions. Or storing a chemical. If you're storing 12 molar HCl compared to storing 6 molar HCl, well, the 12 molar is going to have faster reactions, forward and reverse reactions happening inside of it, so it's a more unstable system. Initially, in reaction B, the system's at equilibrium, but where the forward and reverse rates are equal. At the instant where the reactant is removed, the forward rate decreases. As more NO2 is produced by the back reaction than the forward reaction, then the reactions start to increase back to the equilibrium point. Now the equilibrium point is lower because there's less matter overall, but they are now at equilibrium where the reverse and forward are equal. Okay. So here's another example. This is rate of reaction if you added the product. So here we add the product, and note we're tracking both the forward and reverse rates. So the forward reaction, I'm gonna make that a lot smaller. So let's go with the backwards reaction. So the backwards reaction here is the one that the N2O4 is a part of. So when you increase the N2O4, you have the initial stress on the system, and then a smoothing out or a gradual decrease in that reverse rate as there is more product formed. So this is going to be our stress, change, and then both of these, we can think about both of these parts are equilibrium. Okay, and there's a removal, blah, 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 same idea. Removal, you have an equilibrium, you take away the N2O4, so the backwards reaction is slowed. Because the backwards reaction is slower than the forward reaction, then the forward reaction starts to give you more reactant for that reverse reaction. That reverse reaction starts to increase in speed or increase in rate, and then the rates become equal again. And you have a new constant value. Always remembering yourself that it's a new value. So the new equilibrium values. All right, so now if you increased the temperature, something interesting will happen. So notice that in the increase in temperature, we are going to get increases in both forward and reverse rate. So both. So what do I want to say here? So because this is one of the things we said earlier is that that temperature affects both forward and reverse reactions. First reactions. But unequally. So here we can see the increase. We have, I'm going to do a green line here for the one reaction, and maybe I'll do a red line because red and green show up nicely side by side. So let's put them side by side. So these should be, of course, on top of each other as close as we can get them. And then both those reactions are at equilibrium. So this is our equilibrium down here. And then we have a stress. Temperature goes up. And we're going to notice that one of the two reactions, so one reaction has a huge change, right? So this is, in this case, the backwards reaction. And then the other reaction has a much smaller change. So let's see if I can do, it has an initial change, sort of initially kind of follows the same path, but then it starts to, that change is slower, and the two start to collide again for until we're back at equilibrium again. So in this case, the forward reaction is, well, let's think about this. Which one is it exothermic or endothermic? Well, it is an exothermic reaction. We said that earlier at the beginning. So because it's exothermic, the endothermic reaction, the reverse reaction, has the, so this is an overall exothermic reaction. And so this means that this one is endothermic. And this forward reaction is exothermic. So the endothermic reaction has the greater effect because the endothermic reaction uses this extra energy. And I really like this graph. I think, like, when you really think about this, this is very interesting. It means that in general, it's probably worth it to raise the temperature of almost any reaction because you are going to force both the forward and reverse reactions to go faster. But the amount of product you might, or the ratio of product to reactant, I guess is staying, well, it could be a new equilibrium, new K. You get a new K. So, but there's going to be some sort of change. We don't have concentrations on this graph, so it's hard to say. And so then, of course, in the reverse case, you would have if you decrease the temperature, then the endothermic reaction is hit harder. So the exothermic reaction is a higher change. I suppose. Okay, well, I'll just leave it there. Okay. Initially, the system is at equilibrium. The rates of forward and reverse reactions are equal. When the temperature is lowered, both the forward and the reverse rates decrease. Because the reaction is exothermic, the reverse rate goes down less than the forward reaction does. Reverse rate goes down less than the forward reaction does. I'm going to think about that one. I'm going to put a little question mark here. I'm going to think about that. Because so when the temperature is increased, both the forward and reverse rates increase because the reaction is exothermic. The reverse rate goes up more than the forward reaction does. I would think that it'd be the opposite, that that if the temperature is lowered, then the reverse rate goes down. Reverse rate goes down more than the forward reaction. It goes up more. Shouldn't it also go down more? Wow. Do I look it up now or do I look it up later? That's the question. Effect dumped here. Okay, so the reaction below it illustrates the concentration change. I like these graphs more. I think these are the better graphs anyways, but these are more interesting to look at. So here we have the concentration curves. So if we have a concentration where we see a sudden jump, so here's a stress, right? So here's the stress. We've added some NO2 to the system, and then these are here's the change. Looking at both chemical reactions. So here's the change, and then these are the new equilibriums. So we can see that in general, this little change that happens, we are going to end up, we did put in more NO2, and we do end up with a little bit of NO2, and we do end up with a little bit of extra N2O4 because the equilibrium had to adjust for this extra matter. If we remove the NO2, then we can see the stress right here as the NO2 has been removed, and then we can see the changes, and then we can see the new equilibrium. All right, another example, here we have N2O4, so we're just increasing and decreasing. So very, very similar, where they are talking about, why are they using rate here? Concentration? This is, it maps onto the rate. Anyways, this is, I do not like this. What is that about? Okay, I might remake this whole thing for next year. I'm starting to have some issues with this this edition. Okay, so N2O4. This is the stress here. So we have a stress, and then we have a response, and that response is the N2O4 getting consumed as it forms extra NO2. And so NO2 is increasing. And I mean, arguably, the rates of forward and reverse reactions, remember that the rate of reaction, where was I? Remember that we can also say that rate is equal to K, and let's just call this K forward, for example. So the rate of the forward reaction in this case is equal to NO2, and we're going to assume it's elementary. And then the rate of the reverse reaction is equal to some K reverse times N2O4. And so they are proportional. So if we have changes in concentration, we can say that they are proportional to the rates as well. So this is okay. They can say this. They can. Should they? I don't know. But they can. They can say that because they are proportional through through the rate laws that we did in the last unit. So at the instant when product N2O4 is added, the forward rate is unchanged as the reactant concentration increases. Through reaction, the forward rate increases to its new constant value. Okay. So from a temperature perspective, we do see some changes here. So because the two rates are dependent on temperature in different ways, one produces temperature, one doesn't. We can think about the increase in temperature as having different effects on these chemical reactions. So another way to think about it is sort of as a thought experiment is to think about if we said earlier that we could treat, in the equilibrium NO2 N2O4 plus heat, right? If we can treat it as a variable like this, then that does kind of indicate that we could kind of in a very thought experimenty way, not a true thing, but we could, I'm going to even write it in gray, the worst color. We could think about this as the rate of the forward reaction is equal to K times NO2 squared, and the rate of the reverse is equal to K times N2O4 times heat, right? So that's kind of like, that could be a nice way to sort of justify why the reactions have a different opinion on the effect of temperature. Now, the collision theory does tell us that any heat increase will increase a rate and will actually change K. But if we think about that you need heat to even get this reverse reaction working, then there's going to be an extra benefit for adding heat. So the reverse reaction, the back reaction under temperature should, I'm assuming this was an exothermic reaction. Let me just see. The reaction is exothermic, decreases, so KEQ decreases when the temperature increases. When the temperature is increased, the system is not at equilibrium under the new conditions, and the NO2 increases to establish a new equilibrium. So this is one way you can identify a temperature change, is that notice there is no spike. So no spike, both change continuously together. And so what we're going to see is that the excess, shouldn't the excess reaction be, we are going to see an increase in NO2, which will increase the forward reaction, but the rate of consumption of the N2O4 will initially be high, and then as that excess is reused up, the reaction will decrease. Okay, yeah, I see that. It's a little bit weird. I don't like this. This is me not liking this. This is kind of, I think that's extra confusing. But it's not incorrect. It's just confusing. Okay. So in the other example here, we can see that they're from the same sort of logic. When we start with a low temperature, we start with a low temperature, then the rate of the reverse reaction will be decreased, or will be hampered. And oh, I just realized that that all this stuff I'm writing is right behind my picture of my face. Sorry about that. So the initial rate will be decreased, and now the forward reaction will start to produce extra N2O4 to compensate, and the N2O4 will increase in concentration, and as it increases in concentration, the rate of the forward reaction will start to increase as well. I would argue that initially we should see, if we want, like this is the one spot where these don't actually apply because there's been a change to K. So I think that's why I'm having some issues. So these don't map as well. So they don't map as nicely because K changes. You know what? This is extra that nobody's ever going to care about. I'm just going to, it's something I care about. I should leave a note for myself somewhere, but you guys don't care. Don't worry about it. Okay, so you have the descriptions down here. So initially the system on the left here is at equilibrium. The N2 and NO2 and the N2O4 are constant. The reaction is exothermic. The KQ decreases when the temperature increases, and when the temperature is increased, the system is not at equilibrium under the new conditions. NO2 is increases to establish the new equilibrium. If we want to think about this, why are they saying that KQ is decreased? This comes from using these equations and how we found our K in the first place. Remember that we found K by saying that the K of, and we'll say this one's forward and this is reverse. So we had to say that K reverse divided by K, or no, it'll be K forward. K forward over K reverse was equal to the product over the reactant. And then that was all equal to our big KEQ. So KEQ is equal to K forward over K reverse. If you increase the temperature up here in this sort of little thought experiment version we had, then that implies that that temperature has an effect on the reverse reactions K. So K reverse is endothermic, so it increases under higher T. If you can wrap your head around that, that's amazing. This is all, I think that's all sort of outside the scope of what we usually cover, but it is there. It's all stuff we've done, and we can explain it. But you know, with just the basic rules and equations that we've established, we can even predict changes in K simply by knowing whether it's an endothermic or exothermic reaction. So yeah, so that's that idea. And I believe that's the last page, so I guess I have a little bit of space here to play around and pretend and talk about some heavy stuff. I will post a assignment that has a whole bunch of these that you can identify and let you play with that over the weekend. And then maybe we'll go through some review on Monday. We have no class on Friday, so we will have some free time there that we can do for that Monday. All right, best of luck to you today. That's the end of today's stream. You can work on the assignment I posted yesterday or the one that I'll post a little later, and have yourselves a great long weekend. Talk to you later.